Today, let us discuss about elementary continuous time signals. Elementary continuous time signals. Now, first of all, we should understand why we should be discussing these signals. Now, in real time, let us say we have designed a controller. Say, let us say a speed controller in a laboratory. Let us say we have a laboratory, and in that we have designed a speed controller. Let us say induction motor. For an induction motor. So the speed controller along with the induction motor is known as an induction motor drive. So we have an induction motor drive. So we want to test the performance of the induction motor. So in the lab, what we do is we have built the hardware and we would like to find out what is the output. And if the output that is coming out from the motor drive meets the specifications. So for that we have to provide inputs. Now these inputs cannot be of some arbitrary nature. It has to be in the form of let us say it can be in the form of a step input or a DC, let us call it as, or in other words it's the DC input that can be given to the motor drive, or it could be an AC sinusoidal input, which can be in the form of an AC. We can have other type of inputs also, let us say a ramp input. A ramp input is some kind of, the graph is something like this. A ramp input can be a graph of this nature. So we may have a, let us say this is the time axis and this is the voltage axis. So these are some of the inputs that can be given to the induction motor drive. Okay. But why I have initially mentioned that we cannot apply any arbitrary input for testing purposes. But in nature, we can in fact apply arbitrary input. Any arbitrary input can be synthesized into a step input or a combination of a step input and sinusoidal input. So any arbitrary voltage can be thought of as a summation of a step input and a sinusoidal input. So which implies that we should study the response of the step input, sinusoidal input, ramp input, and a few other test signals that are available. So in signals in systems, it becomes imperative that we study the how to model the step input, how to model the sinusoidal input. So modeling of these inputs are known as signal modeling. Signal modeling is nothing but finding some mathematical expression or an equation for each of the elementary signals. Okay, that is what is known as the signal modeling. Now, in industry, it always happens that the hardware is built. Before the hardware is built, we, the induction motor drive is actually modeled in software. It is modeled in a software, and the output is actually the performance of the model that has been developed in a software is first tested using inputs, and these inputs will be again the step input, which can be easily generated using some circuits, Step input is nothing but a DC input. Again, sinusoidal inputs can be generated using oscillators, generators, AC generators. So first, even before we actually develop the hardware, we develop the software model and then we test and we find out what is the output. Once this software model gets the produces a desired output, then we actually build the hardware model for the software model and then we do the testing. So here in the laboratory, when we do the testing, we get the output and we want to see that the output that we got from the software actually matches what we got from the hardware. So this, the block here that is represented here is actually represents a software model, which are otherwise known as the system model. This system model is again some mathematical expression. Okay, so more popularly known as a transfer function. So this now this makes us understand the importance of studying elementary continuous time signals. The mathematical form of these signals is what we are going to study in this lecture. Okay, so let us now go to take up each of these signals and try to develop a signal model. It's taking some time. Let us do the signal modeling for each of the elementary signals. So the first signal that we are going to take up is the step input or the step function. The signal model or the step function is defined as u of t is equal to 1 for t greater than or equal to 0 and is equal to 0 for t less than 0. Now let me draw the graph for this. So I said this is t is equal to 0. So prior to t is equal to 0, the value is going to be 0. The amplitude is going to be 0. And after t is equal to 0, it is going to have an amplitude of 1. So this is how the signal is modeled. The step function is modeled. Now let us take the next signal, elementary signal, which is the ramp signal. The ramp signal, the ramp function, or more specifically it is known as the unit ramp function, because the slope will be equal to 1 here. Let us see how it is. So first let us model the signal. The signal modeling here is r of t is equal to 1 is equal to t for t greater than or equal to 0, and it is equal to 0 for t less than 0. And the graph for this is going to be, the sketch for this is going to be something like this. It is going to be like this, and you can very well see that the slope is going to be 1. So when the slope is equal to 1, that is, let us say, let me take a point here which is 1 here, and if I take a point here, it is going to be 1. The slope for this is going to be 1. When the slope is equal to 1, we call this ramp function as a unit ramp function. Okay. when if the slope is something other than 1, we don't call it as a unit ramp. And you should know that if you differentiate this ramp function, we get the unit step function, okay, or the step function, uh, the ramp function can be got as an integration of unit step function, which is ranging from 0 to infinity. Okay, so why 0? Because the signal does not exist before t is equal to 0. So the signal actually exists only after t is equal to 0. That is the reason why you are having the lower bound, the lower limit happens to be 0. So this is something about the unit ramp function. Okay. So the next function, let us take up the unit parabolic function. The unit parabolic function is the third elementary signal that we are going to study. The unit parabolic function. The unit parabolic function is defined as p of t. When the unit step function is denoted as u of t, and the unit ramp function was denoted as r of t, and the parabolic function is represented in p of t. The p actually the letter of the parabolic stands for. That is the reason why it is called as p of t. So this is nothing but is equal to t. The signal model is nothing but t squared for t greater than or equal to 0, and it is 0 for t less than 0. So you can draw the plot for this. The plot for this will be as follows. It will be a parabolic plot, okay. And so for when t is equal to 1, the value here is going to be 1. When t is equal to 2, the p of t value is going to be 2. That is the reason why this one is known as the unit parabolic function. Okay, and extending the same logic for a differentiation and integration. So if you try to differentiate this, suppose if you try to differentiate this, okay, let us put 2 here. Okay, so when you try to differentiate this, it becomes 2t divided by t, so you get t, which is nothing but a ramp. So if you want, you can if you want to generate a parabolic function from a ramp function, what you have to do, you have to integrate the ramp function. So when you integrate the ramp function to limit 0 unto infinity or t, so you end up getting t squared by 2, which is the parabolic function from the ramp function. So let me go back and do some changes here also. So let me erase this and put t. Okay, so far we have seen 3 functions. Now let us see the next function, which is not very important function, which is known as the impulse function. Okay, the fourth elementary signal is the impulse function, and it is defined as, the impulse function is defined as delta of t. Okay, and the definition is, the impulse function definition is given as, when you integrate it between limit 0 minus infinity to plus infinity, you get 1. dt is equal to 1. This is the definition for a impulse function. Okay, and the way we represent a impulse is graphically, it is something like some rectangular, some kind of a spike here. Okay, so let me call this the time period. This is the time axis. The time, the small interval of time, let us call it as delta, and the amplitude is called, it is actually, the amplitude is 1 by delta. So when you multiply these two, you get 1. Okay. So essentially what you are doing here by integrating this, the integration of this is essentially the multiplication of the time axis versus the amplitude. Okay, the multiplication of time and the amplitude is actually what the meaning of the integral. So the meaning, that actually obviously will be equal to 1 by looking at the amplitude and the interval delta that is given here along the time axis. Okay, so this is how it is graphically represented. The impulse function is graphically represented. Okay, the next one what we are going to see is, okay, let us now uh, look at some of the properties of the impulse function. Okay, so some of the properties will be very useful with solving problems. So you need not necessarily go through the derivation of each of the properties. Just we state the properties, and then we will see, we'll take up a few problems and work it out and use these properties in order to solve the problem. Okay, so the first property is integral minus infinity to plus infinity delta of t, x of t into delta of t, that will be equal to dt, that will be equal to x naught. Dt is equal to x naught. Of course, we will try to see how it is possible, how it is, how this integral got evaluated to x naught. We just, though I mentioned that we will not derive, but for better understanding and for remembering, let us try to derive this and see how we are able to get x naught. Okay. So let us do that. Now, before we actually try to find out how the integral will be evaluated to x naught, one thing we should understand is that x of t into delta of t is x naught into delta of t. Now this, if you want to remember how this was made possible, what you have to do is, you have to write like this, x delta minus 0. So whatever the value here after the minus sign will have to be substituted here. That is how this gets operated. A function x of t, when multiplied with a delta function, it gets evaluated to this. That is, what happens is, we have to write this part like this, and then what we do is, whatever the value here in this case it is 0, in not all cases it will be 0, whatever the value that was found to be here will have to be substituted here. That means we get this. Okay, so let us go back to the property. So what I mentioned was, so it was negative infinity to positive infinity x of t into delta of t dt, and this will become negative infinity to positive infinity x naught into delta of t dt. Now this is a constant. Earlier it was a variable, a function of t. X of t was a function. Now after doing this operation on this, I did this operation. When we did this operation on this got evaluated to this. Okay. Now this expression is having a constant times delta of t. So what I can do is, I can take the constant out of the integration, and I have delta t here. Now, by the definition of impulse function, this integral gets evaluated to 1. So what you are essentially having is into 1, which is equal to x of x naught, which means this got evaluated to this. So I hope this property is clear. Now let us look at just a logical corollary of the first property. The second property is integral minus infinity to plus infinity x of t delta t minus t naught. Now you can very well see that as I said, whatever the value that is present here will have to be substituted here. This value will have to be substituted here. Once when you substitute, this entire thing becomes a constant. It gets evaluated as a constant, becomes x of t naught into delta t minus t. Now this, see, we are having a delta function is represented like this. So when I represent this, it is actually delta of t. So when I do it, we have not actually touched upon the shifting of the waveform, but take it from me that when you shift this waveform by t naught units, that is a function. Okay, let me elaborate this. If I have a function x of t, let us say I have a curve, have a waveform something of this nature, then x t minus t naught. Let us assume the t naught is positive. Okay, let us say I am having it's a positive value. Then the entire wave gets shifted by t naught units. Okay, this wave got shifted to by t naught units. Okay, and in this case, when when if I shift this by t naught units, I'm assuming that t naught is positive here. Then it becomes the way or the impulse. This got shifted there, and now I am having the impulse at t naught. Earlier the impulse was at t is equal to 0. Now it has got shifted to t is equal to t naught. Now you should understand the limits of this integration is negative infinity to positive infinity, and it is able to cover in this range. I am still having t naught, and because I am still having t naught, this entire integral becomes 1. This gets evaluated to 1, so I am getting a value of t naught. So this integral got evaluated to t naught. Okay. I hope this explanation is clear. Now next is let us take the next property. Okay, the next property, let us take the next one. It is, let us, if you have a delta a of t, then this becomes delta or delta 1 over the magnitude of a. The a in this case may be positive, negative, or negative. Can be a can be positive value or a negative value. Okay, say suppose for as an example, let us say example we are having negative 2t. This I can write it as 1 divided by magnitude of negative 2 into delta of t, that is equal to 1 divided by 2 into delta of. So this is one of the important properties. Okay, now suppose let us say let us say let us try to evaluate this negative infinity to positive infinity x of t delta of v of t dt. Now this I can very well write it as minus infinity to plus infinity x of t 1 divided by a magnitude of a delta d dt. Now I know this I can write it as this is a constant value, so I can take it out of the integration. So minus infinity to plus infinity x of t delta of dt, and this I can write it as 1 divided by a. You know this gets evaluated to 1. Okay, this actually gets evaluated to 1. So which means I get the final response, the answer for this is 1 divided by a. Okay, so let's try to take the next property. Suppose if I am having a signal Let us call the signal as x of t. Let us say I am having a okay, excuse my drawing, but anyway, okay, x of t. So let us say I am having a signal of this nature, some waveform. Okay. Now, if you see the negative, the time axis is t and the y axis is x of t. Now this t is actually a dummy variable. I can very well change. I can make it instead of d, I can put it as p also. So I can say instead of t, I can put it as p. Okay, and still I can have the same wave. Okay, so it is the same wave. So you must understand this t is actually a dummy variable. It can be the t can be replaced with either p or tau or x, sorry, or w or k or whatever it is, and but the waveform still remains the same. Okay. The same thing implies even to, let us say I am having a delta function. Okay, the delta function is actually represented by an arrow. Okay, pointed arrow pointing upward. Okay, let this be delta t. Now, if I reflect, okay, there's something else also I think I have to introduce before we actually take up this. Let us say we are having a function, okay, x of t. Uh, let us say it is some function of this nature. Okay, and what is then x of negative of t? For this, I'm talking about this, not this one. I'm talking about this function. Though I am using the same x of t, maybe for to avoid confusion, what I can actually use some other. Okay, let me use some other some other index value. Maybe I can use it as x of k. Then x of negative of k is nothing but a reflection of the mirror image or the reflection along the. It has to be reflected along the y-axis. Okay, so when I reflect it along the y-axis, this is a mirror actually. This I take it as a mirror. The y-axis is taken as a mirror, and when this is actually uh, when it is focused on the mirror on the other side, okay, so you get a mirror image. Okay, so this is essentially x of negative of k. As I said, this k is actually some index number which can be replaced by even t or tau or p or whatever. Okay, so this is important. Why so is, if I try to reflect this on the x-axis, what I will get is the same thing. Okay, it is again the same. This is actually x of negative of t, sorry, delta of negative of t. So you can see that delta of t is equal to delta of negative t. There is no change at all, because, but on the contrary, if I have, so let us say on the contrary, if I was having something like this, suppose I was having a delta function. Let us say there is a delta function here at an instant t naught. Then when I reflect it on the y-axis, what I will be getting is something like this. Okay, so negative t naught. Okay. So this is delta of t minus t naught, whereas this one is okay. This is actually delta of minus t naught. Okay, this is what it is. So delta of negative t, negative d naught. Okay, so you can see the differences. In our case, in the example that I'm going to take up, I am interested only in the impulse function that is along the y-axis, and when I reflect I find that delta of d is equal to delta of negative t. So I'm going to use this. So what we are seeing is we are having a wave. Let us call this as, we saw that there was a wave, okay, waveform, and let me call it as x of tau. I said that t can be replaced by any index number, any variable, okay, it need not necessarily be t, okay. And let me also call this as delta of tau. So when I reflect the when I reflect it along the x-axis, I get delta of t minus tau. Now if I shift it in the positive direction by some through some distance, let's say t from the origin, let me say I have shifted it through some distance t, then I get, what I get is delta of t minus tau. Now let me this, what I have done is I have shifted it, this I have taken this wave and shifted this by shifted it in the positive y direction, positive x direction, positive x direction, x axis. I got this. Similarly, if I shift this waveform, if I take this impulse and shift it by, let us say I shift this by the same distance t, and what I get is delta of tau minus t. So if you notice, if you take this waveform and it's the same, there is no difference at all, okay, which means, to conclude, I can safely conclude that t minus tau minus t is equal to delta t minus tau. Okay, so let me go back to the problem. It is negative infinity to positive infinity x of tau. I want to evaluate this. Here, if you notice, t is not the variable here. Okay, it's not the differential. We are not trying to integrate with respect to t. We are trying to integrate with respect to tau. Okay. So how to evaluate this? I can evaluate this by just doing some manipulation. This is equal to x of tau into delta tau minus t into d tau. Now you should notice I have replaced this with this by virtue of this expression. Okay, I've just replaced this by this. Okay, now what I can do is, I know there is a property when I multiply the x of tau with delta tau minus t, I get x of t into delta tau minus t d tau. Now this is a constant because the entire integration is with respect to tau, not with respect to t. So I can take this out of the, and what I get is tau minus t, which is nothing but this is nothing but x of t, because this will become equal to 1. This integration will become equal to 1. So what I finally end up getting is x of tau. Okay, sorry, x of t. So this will be equal to x of t. Okay, so this expression is known as convolution integral. Okay, so let us now take up another function. Let us take another function. This function is known as, I don't remember which number it is. Okay, whatever it is, this is another rectangular, this is another signal function, which is known as the rectangular pulse function. Now the rectangular pulse function is denoted as the graph for this is this is the graph. Okay, so the amplitude is 1, and here it is actually the t is negative of half and positive half. Okay, so it is denoted as some symbol this of t is equal to 1 for equal to half. Magnitude of t is less than or equal to half, and it is 0 for magnitude of t greater than 0. You know what it is, right? So this implies that when t lies between minus half and plus half, we have the value 1. Okay, when t is greater than half, or t is less than negative half, we have a value 0. Okay, so that is the meaning of this. Okay, so this is the rectangular pulse function. We take up the next function, which is known as the triangular pulse function. Triangular pulse function. Now this triangular pulse function is nothing but okay, let me draw that. Again, okay, let us call it as a here, and let us call it as okay, a here. So it's negative a and positive a, and this value here is 1. The amplitude is 1. Okay. And the mathematical expression for this is some triangular a subscript of a of t is equal to 1 minus magnitude of t divided by a for less than or equal to less than or equal to a. Okay, or 0 for greater than a. So it is not having any value. Okay. So this expression is actually the triangle part. Okay, the triangle part is actually represented by this function. Okay, we will try to understand why this expression represents the triangle later. But for now, you can just take it as negative of 1 minus negative of t by the magnitude of t divided by a is represents this the plot here. So the next one is the signum function. Let us quickly see what is the signum function. Signum function. The signum function is nothing but the graphical plot for this is something like this. Okay, I have one here, amplitude, and it is negative 1 for t less. So for t it is 1 for and for t greater than 0, and it is negative 1 for t less than 0, and it is the symbol for this is signum of t. Okay, the signum of t is equal to 1 for t greater than 0. I can also write signum of t as 2u of t minus 1. Now you can see why it is so, because if you try to plot this, you will understand that it's nothing but the signum function. Okay, so you can do it yourself. It's not very difficult. So we will take up other functions later as we go along. So in our next lecture, we'll take up a few problems and then work out the problems, and then after that we move forward. Okay, thank you.